topic for today is a special ratio that is found in a right triangle. So we will be talking about the TOA of the mnemonic SOHCAHTOA that we'll be discussing for a few days. So first of all, we're going to start by going to a real quick GeoGebra exploration. And the focus of today is not on the hypotenuse, but it's on the opposite leg and the adjacent leg. And when we have a 30, 60, 90 triangle, it does not matter how large we make the opposite leg and the adjacent leg, because when we divide the opposite by the adjacent, we get 0.577 as the ratio of the opposite over the adjacent, or the division of the ratio of the opposite over the adjacent. So we can make the triangle larger, and we can make this triangle teeny tiny, and we always get that same ratio for the opposite over the adjacent. That's because all of these triangles are similar. We're just changing the scale factor when we reduce it or enlarge it, but it will still have that same ratio when it's all said and done. If we change the angle measure to be a 40-degree angle, for example, and look at the ratio of the opposite divided by the adjacent and divide it out, it does not matter how big that triangle becomes or how small that triangle becomes. If the angle stays the same, that opposite over adjacent is always the same number. And in this case, we've rounded it to 0.839. So when we go back and talk about that special ratio, we give it a name called tangent. The tangent of an angle is the length of the leg that's opposite from that angle divided by the length of the leg that is adjacent to that angle. So remember that opposite means across from, adjacent means next to, touching, is part of that angle. So if I want the tangent of angle A, I would take the value of the leg, the length of the leg that is opposite that angle, over the length of the leg that is adjacent to it, that's next to it. Because we're mathematicians, we like to save time and not write things completely out. So we have decided that we will abbreviate tangent of angle A to be simply tan of A. And the tangent of angle A is always the opposite side of angle A, the opposite leg, divided by the adjacent leg. So for today, because we're talking about the tangent, we are not concerned with the hypotenuse. We ignore it for today. Angle A is here. It is the side, or the lower acute angle, and the opposite side of A is BC, which has a length of 12. The adjacent to angle A is AC, which has a length of 16. So the tangent of angle A will be equal to 12 divided by 16, which is the same thing as 3 divided by 4, which is 0.75 as a decimal if we divide it out. If we want to find the tangent of angle B, now we want to find B first and decide which side is opposite angle B. And that's the 16. And which one is next to it? Again, we're ignoring the hypotenuse for today. That is not the adjacent leg. The leg that is adjacent to it is the leg that helps make that angle. So 12 is the adjacent to angle B. And so when we want the tangent of angle B, we are now wanting 16 divided by 12, which reduces to 4/3, which reduces to 1.33 as a decimal to 2 decimal places. So where do these angles come from? Well, since we know that these ratios are consistent. It doesn't matter how big the triangle is, as long as it has the same angle, it will have that same ratio of opposite over adjacent. Back in the old days, we used to have a table in the back of our textbooks, and that table would have all the angles between 0 and 90 degrees, and it would have a listing of the tangent of those angles. That is now stored in a scientific calculator. So when we're looking for the tangent of 12 degrees, for example, we will be able to press tan of 12 degrees in our calculator, provided our calculator is in degree mode. So let's bring up a scientific calculator, a graphing calculator, and turn it on. On a scientific calculator, you can generally see what mode it's in. There will be a DEG, a DRG, or a D often in the window, really small and tiny. In this case, on a graphing calculator, you need to press the mode button and make sure that the degree is shaded, that is the option that you're using. And we press second and quit to get back. So since I'm in degree mode, I want to press the tangent button, which is abbreviated TAN, and then I want to type 12. If that's all I'm doing, I don't have to close the parentheses, but I can. And I press enter to request it, and I get 0.212556, which rounded to 4 decimal places is 0.2126. So this big old giant table has been stored in your scientific or your graphing calculator, and you don't have to go back to the old days of looking things up from a table. So when we want to find the tangent of 77 degrees, now rather than go dig out a table, we simply press tan and 77, making sure that our calculator is in degree mode, and we get 0.4331 if you want it to 4 decimal places. That is simply the ratio of the opposite leg divided by the adjacent leg for that particular angle. All right, so now we're ready to start solving problems involving trig, or right triangle trigonometry. All right, so here's our angle. The angle is 67 degrees. So we know one piece of information, we know a second piece of information. We have 12 for one of the legs, and we have x for the other leg. So we know that the tangent of an angle is the opposite over the adjacent for that angle. The angle is 67 degrees, so we write tangent 67 degrees, and that is the ratio of the opposite divided by the adjacent. And again, we are ignoring the hypotenuse for today. So the tangent of 67 is x divided by 12, or x over 12. Since x is being divided by 12, we want to get the x all by itself. So before you plug anything into your calculator, we're going to multiply both sides by 12 to get the x by itself. So we know that x is 12 times the tangent of 67. So we break out our good old trusty calculator again, and we type in 12 times the tangent of 67 degrees. If this is all we're doing, we don't have to close the parentheses. And we find out that x has a length of 28.3, whatever unit it happens to be, if we're rounding to 1 decimal place. For our next example, we do the same thing. We set the tangent of the angle, in this case it's 34 degrees, equal to the opposite divided by the adjacent. x divided by 18. So to simplify this, we get the 18 to be multiplied by both sides, and 18 times the tangent of 34 is equal to 12.1 units. Had I wanted to multiply the tangent of 34 times 18, order of operations says that we can do that. We can switch the order of a multiplication problem without impacting it. So the key to that is to remember to take the tangent of 34 and then close your parentheses. Otherwise, it will try to take 34 times 18 and then take the tangent of that angle. So we want the tangent of 34 times 18, and you should get the same result, provided you close your parentheses. So the next example has a slight twist to it, because we want to figure out what x is, and this time the opposite from our angle is 16, and the adjacent is our x. So when we set up our ratio, the tangent of 27 equals our opposite over our adjacent. We have a different look to this because now the 16 is being divided by x. And it's crucial that you write your equation out. Don't just start plugging numbers into your calculator. It's also crucial that you solve for x before you plug anything into your calculator. So what I like to do when I see this is I like to make it into a fractions equal to a fraction. That means that we would cross multiply x times the tangent of 27 is equal to 1 times 16. And then we want to get the x all by itself, so we'll divide by the tangent of 27, and x becomes 16 divided by the tangent of 27. Once you've done enough of these problems, you'll start to recognize that the tangent of 27 and x are going to switch positions. So you could jump from this step down to this step and say that x will be equal to 16 over the tangent of 27. So breaking out our calculator again, 16 divided by the tangent of 27 and I have two division signs here, we'll clear one out, is going to be equal to 31.4. So the length of our adjacent leg is about 31.4 if we're asked to find it to one decimal place. To find the exact value of a special right triangle, when you see the word exact, that means that we do not want the decimal equivalent. Instead, we want to have it in square root form. So it does not matter what one of your sides is on a 30, 60, 90 triangle, because they're all similar, and they will all scale up or scale down to that same ratio. So we'll pick a random number. Let's say that we pick 4 for our hypotenuse. Since the hypotenuse is 4, to get to the short leg, we divide by 2 and have 2 for our short leg. To get from the short leg to the long leg, we multiply by the square root of 3. So we will have 2 square roots of 3. So to find the tangent of a 30-degree angle, we want the opposite divided by the adjacent. The opposite of the 30-degree angle is 2. The adjacent to the 30-degree angle is 2 square roots of 3. Since we have 2 divided by 2, it cancels, so the tangent of 30 is 1 over the square root of 3. But we don't like to leave an irrational number in the denominator, so we multiply by the square root of 3 over the square root of 3 to rationalize that denominator. In the numerator, we get 1 times the square root of 3, which is square root of 3. A square root of 3 times a square root of 3 is a square root of 3 squared, so it's plain old 3. And that's our exact value of the tangent of 30. There are no decimals. To check your work, take the square root of 3 divided by 3 in your calculator and see what you get. So the square root is the shift or second of your squared key in many cases. So the square root of 3, we have to close our parentheses to say that we're finished with the square root, and then we say divided by 3, and we get 0.5774 to 4 decimal places. To verify that that is the actual answer, we can simply press tangent of 30 degrees, and we should get the same result, 0.5774. So our answer checks. The next thing to be aware of is the angle of elevation and the angle of depression. So if you've ever flown inside of a plane and looked down on at something, or been on a tall tower or high in a tree, you would be looking downward at an angle of depression. If you are ever lower and looking upward, that's the angle of elevation. And because these lines are parallel and they're cut by a transversal, the angle of depression and the angle of elevation are equal, are congruent. So if we are asked to find out how far an airplane is from an airport, and the airplane is flying at a height of 3 miles above the ground, you can start to sketch a picture of it. If this dot is your airplane, and it's 3 miles above the ground, and it is flying downward at an angle of depression of 2.5 degrees, if it had been flying level, we go 2.5 degrees down from that. And I've run out of space. There's no way that this is going to be an accurate representation, so this is not to scale. In fact, I'll show you the quick build I had. Okay, so this is certainly not to scale because this is not going to be a 2.5 degree angle. But we get something that looks like this. And we want to know the ground distance between the airplane and the airport. So when we're looking for that ground distance, that's our x. The angle of elevation or depression is 2.5 degrees. So the opposite is the 3 miles. The adjacent is the x. We're using the tangent, which is the opposite over the adjacent, to figure out what the distance is between that airplane and that airport is via the ground. So tangent of 2.5 is equal to the opposite divided by the adjacent. And when we work these enough, we'll find out that the x and the tangent of 2.5 are going to switch places when we solve this. So we want to take the 3 divided by the tangent of 2.5 degrees. And again, because this is not to scale, it will not look right. But 3 divided by the tangent of 2.5 gives us 68.7 miles. So this is roughly 68.7 miles away.